stuff, I have a more general result called Axer's theorem. And after I finish that, I'll move on to the study of Dirichlet series as a topic and so on. All right, so recall the following two main ideas that were needed. So m of x equal to little over x, implying summation mu of n over n 0 involved two ideas. Right? What were the two ideas? One, the fact that if you sum mu d integral part of x over d, d less than or equal to x, this is always 1. So this is coming from the fact that summation mu d dividing n is 1 at n equal to 1 and 0 elsewhere. And the second idea was that summation mu d fractional part of x over d was also little over x. Okay, so if you look at these two, basically what we then do is we look at x times mu n over n, n less than or equal to x, and write it as summation mu n integral part of x over n plus summation mu of n fractional part of x over n. The little o of x is this is little o of x. So what you're saying is m of x, which is the sum of the Mobius function being little o of x, if I put this weight, fractional part of x over n, it doesn't affect it, it'll still be little o of x. This one has a collapse and it only gives you 1. But in order to prove this, you only need to know that x times this is little o of x. We don't need to, so we need to know that this is little o of x. This is guaranteed to be little o of x. This need not be actually 1, it is. But even if you had a weaker estimate, which gives you little o of x, you will still win. The final thing will still converge to 0. So what I'm trying to say here is that provided you are able to establish a result like this for other arithmetical functions which take value 1 and minus 1 with almost equal frequency, you don't need anything as sharp as this, because this is very special for the Mobius function. All you need to know is that this also is little o of x. There is enough cancellation. Then it will still work. Okay. So let's consider the following example. So instead of mu of n, consider the Liouville lambda function, in a sense more natural. So what is this Liouville lambda function? It is lambda of n is minus 1 to the total number of prime factors of n. So that's your Liouville lambda function. It's more natural. So it's minus 1 to the total number of prime factors of n. So it's totally multiplicative. Lambda of mn is lambda of m times lambda of n for all mn. It's not even, you don't even need m and n relatively prime. And it takes values plus minus 1. There is no 0 coming in here. The Mobius function takes value 0 at the non-square free numbers. So it looks artificial, but that is what enables you to go through this fantastic cancellation. Okay? So you've got this Liouville function, which is more natural. It's plus 1 when a number has an even number of prime factors, and minus 1 when it's got an odd number of prime factors. We'll talk about the Mobius, about the generating function of lambda and later, but let me just say here, okay, this function satisfies the following. One, that if you look at summation lambda, before that, we should say that if you sum lambda of d dividing n, you get 1 if n is a perfect square, and 0 otherwise. So this little lambda function is its summation is the characteristic function of the perfect squares. Now this is easy to see because if I write n as p1 to the e1, p2 to the e2, pr to the er, then your summation lambda d dividing n is product over all pi, 1 minus 1 plus 1 minus 1 and so on, right? Because that's minus 1 squared. And how many times do you go? The last term is minus 1 to the ei. So this is at an odd position, this is at an even position, this is at an odd position, and so on. So if you do this summation, you'll get either 1, 0, 1, 0, depending upon whether you have your ei is even or odd. If ei is even, you will get 1. If ei is odd, you will get 0. Now, this is a product. So the product becomes 0 if any one factor is 0. So the product will be 1 if every factor is 1. And every factor is 1 means every ei must be even. And if every ei is even, that means the number is a perfect square. So that's why this summation is 1 if n is a perfect square and 0 otherwise. Okay, it's purely because of this. All right. So what does that mean? All right, this function satisfies this. So 2 implies that if you look at summation lambda d, integral part of x over d, analogous to this. This is the same as summation n less than or equal to x, summation lambda d dividing n, right? Because if I flip, I bring the d here, then I have to count the number of n up to x, which are multiples of d, and that is your integral part of x over d. But this sum, in the Mobius case, was 1 at n equal to 1 and 0 otherwise, and that's why it gives exactly 1. But this one is 1 at the perfect squares and 0 otherwise. So this is actually the integral part. So if you want, you can write this as the sum of the characteristic function of the perfect squares, right? This is the characteristic function of the perfect square. So this is integral part of the square root of x. There are that many perfect squares up to x. So this is an example of a very naturally defined function, 1 and minus 1. But when you sum this, when you take a sum like this, it's not giving you 1, it's giving you something of order of magnitude square root of x. But that shouldn't bother you because ultimately when I want to do x times lambda n over n, I only want this to be little o of x. I don't have to have this tremendous cancellation to get 1 here. That just turned out to be a coincidence in this case, or turned out to be a special property. Okay, so this would work. Okay. Now let us look at the generating function. The Dirichlet generating function of lambda n is summation lambda n over n to the power of s. Now let us look at this. Right? What is this equal to? Well, what I'm going to do is I'm going to take this and multiply it by zeta s to get this property. So this is going to be summation lambda n over n to the s times summation 1 over n to the s. And that's equal to, remember when I have an over n to the s bn, I do the Dirichlet convolution, ad bn over d. So this is summation m from 1 to s of the convolution of lambda and 1, which is summation lambda d dividing n divided by n to the s. That's what you will get by multiplying these two as Dirichlet series. Right? In their domains of convergence, s real part s greater than 1. Right? But that is the characteristic function of the perfect squares. Therefore, this gives you summation 1 over n to the 2s, which is zeta 2s. Therefore, yielding
summation lambda n over n to the s has generating function zeta 2s over zeta s for a real part greater than 1. So we'll call this 3. So this is the generator. So the Mobius function, its generating function is 1 over zeta s. And that 1 over zeta s has a 0 at s equal to 1 because the zeta function has a pole. But zeta 2s over zeta s also has a 0 at s equal to 1 because the zeta function has a pole, except the coefficient now will be pi squared over 6 for zeta 2. If you expand it as a power series around s equal to 1, then you'll just get s minus 1 plus dot dot dot. The coefficient of s minus 1 will be 1. Here you'll get pi squared over 6s minus 1, and then you'll get a power series. But what this says is, if you go through the same analytic proof, there is no contribution coming from s equal to 1 because it's a 0. That's the reason why this sum is little over x. So here also, this will yield summation lambda n less than or equal to x to be little o of x. In fact, it will yield capital O of x over e to the c square root of log x. I mean, that's what you will get by going through the proof of the prime number theorem. But instead of zeta prime over zeta, you will apply it to this one. So you have, instead of m of x equal to little o of x, you have this equal to little o of x, and then you have this, which is little o of x. Therefore, what we need is, will this equal to little o of x imply that multiplied by the fractional part of x over n to be little o of x? And if that happens, that sum is little o of x, which means x times summation lambda n over n will be little o of x, which means this sum will be convergent to 0. That's what you expect, because as I let s tend to 1, the right hand side tends to 0. But you know, this limiting behavior is what we are trying to establish as deep as the prime number theorem. So we say here, if we now have that 4 implies summation lambda n fractional part of x over n is little o of x. If this is true, then x times summation lambda n over n less than or equal to x is summation lambda n integral part of x over n less than or equal to x plus summation lambda n fractional part of x over n less than or equal to x. That's the integral part of square root of x plus little o of x will be little o of x. That would imply that the sum lambda n over n from n equal to 1 to infinity is 0. So the question is, can we move from this to this? And if so, we should be able to do it for fairly general sequences. So that is the thrust of this theorem that I want to state and prove, and you can apply it in many situations. So this is called Axer's theorem. And so this is taken from Hardy's Divergent series, a very beautiful book. In fact, one of my dreams, I don't think I'll ever realize that dream, is to give an entire year's course on Divergent series from Hardy's book. I would find it how many people I can get interested to take such a course. I mean, it's beautiful. It's all classical stuff here, okay? And according to Littlewood, who has written this preface, this was really Hardy's favorite book among all the books he wrote. Okay, so Axer's theorem, taken from Hardy's Divergent series. So it says the following. Let A of n be a sequence of reals, of course, satisfying, actually you can even apply it for complex, summation A of n is little o of x. Okay? All right, so A of n is like your mu, it's like your lambda, and so on. Okay, so the sum is like this. Let chi of x be of bounded variation in every finite interval. You're not saying infinite interval. So it's not, we're not saying it's a bounded variation on 1 to infinity. Now I have two conditions. Suppose either pair, the following conditions are satisfied. So I have a pair of conditions, but either one of them. A, the function chi of x is bounded, and the sum of the absolute values of the a's is capital O of x, not little o, capital O of x. So the a's are bounded on average. Or B, chi of x is O of x to the alpha for 0 less than alpha less than 1, and A of n is bounded. But this is stronger than saying that the sum of the absolute value of the a's is O of x. Then the claim is summation a n chi of x over n is little O of x. So this is Axer's theorem. You can get quantitative versions of Axer's theorem, but I just want to highlight the general principles here. So we've been applying Axer's theorem with chi of x being fractional part of x, which is the sawtooth function, and that's a bounded variation on finite intervals. And we applied originally a n with mu, and I indicated how to do it with lambda. But now that you can apply it to many other situations, so that's why I'm stating this. Okay. So, and we'll prove this. The proof is quite easy. It follows the proof that we had before. So proof. So let delta be in 0, 1 to be specified later. Decompose summation, we'll call this sum S of x. Okay. So we decompose this into two parts, right? But A sub n to be the partial sum of the ANs. Okay? Now, what can we say about S2 or sigma 2? And sigma 2, that has got an, right? So this is an minus 1 chi of x over n. So this just becomes a integral part of x, chi of x over, these are just the endpoints, maybe I should put integral part here. All right. So I probably am off by 1 because it's that plus 1. The integral part means I go to the left, so I got to go on to the right. Doesn't matter. This is going to be more bounded. Plus summation an chi of x over n minus chi of x over n plus 1. So this is simple. X minus 1. Yeah, these are the endpoints, and this is it. All right, now, what can you say about this quantity? You see, this is your AX. So this is little o of x. Chi is bounded. So let us take the case A first. Okay? So we'll look at the case A first. Okay. The chi function is bounded. This is going to be O of 1, little o of x, O of 1, little o of delta x, but little o of delta x is absorbed by little o of x. Because little o of delta is the same as capital O of delta, so this is absorbed. So this together is little o of x. Okay. So this in this case, the sum in 9 is little o of x coming from this part. I'm now assuming A. Right? Little o of x coming from this part. And what can you say about this? This is little o of x. Because it's really little o of x times delta. It's little o of delta x. Right? But so that means it's epsilon times delta x. But this is less than or equal to that's the total variation of the function chi on the interval from 0 to 1 over delta. These are points on the interval starting from 0 or 1 to 1 over delta. So this is the total variation of the function chi on the interval from 1 to 1 over delta. So this is a function of delta alone, the function of delta alone. So little o of x has got an epsilon in it. So the moment I know, I'm given a function of bounded variation. So that means I'm told something about the size of this total variation function. So I will now choose a delta that goes to 0, so that 1 over delta can go to infinity with x. It's not infinity yet. It's large. But still that multiplied by this small quantity is still small, right? I mean, like I can choose this to be no more than 1 over square root of epsilon, for instance, so that this product is like square root of epsilon. So this can still be made little of x by choosing delta greater than 0, small enough. Okay, so that's what it's small enough to get this, but I still want, it's not too small. But what about the first side? Note that sigma 1 is simply summation an chi of x over n less than or equal to x, and delta x. So that's equal to the chi is bounded, so pull it up, and then I have summation absolute value of n less than or equal to delta x. But then that is equal to little o or capital O of delta x. But delta is small. We're choosing delta go to 0. So this is little o of x. So delta is chosen to be much smaller. You start with an epsilon and then you choose a delta as we did here. So that is using these two conditions. Now, if I had the other two conditions, chi of x is O of x to the alpha, okay, see. So if B is satisfied, then what can you say about sigma 1? Then sigma 1 is, but now the A is bounded. You don't worry about the chi. The A is bounded. So if I look at the A and chi of x over n, the A comes out, and now this is going to be summation chi of x over n less than or equal to delta x. But the chi function is capital O of x to the alpha. So your x to the alpha comes out. And I'm now summing 1 over n to the alpha for n less than or equal to delta x. And what is the size of 1 over n to the alpha up to some point t? By the integral test, it is the integral of t to the minus alpha. So it's t to the 1 minus alpha divided by 1 minus alpha. So keep that 1 minus alpha in the column if you like. So that's equal to capital O of x to the alpha delta x to the 1 minus alpha divided by 1 minus alpha. But alpha is given, it's a fixed number. So you can absorb it in here. It's a fixed number, like 1/3 or something. Okay? So this is a fixed constant. So this is going to be equal to capital O. The x to the minus alpha will be cancelled. So you actually get delta to the 1 minus alpha times x, sorry. X to the alpha, x to the 1 minus alpha. So this is little o of x. Now, of course, it's not just delta x, but delta, the set could be like square root of delta x, or delta to the 1/3 x. So this is still little o of x by letting delta small enough, by choosing delta small enough. All right, now what about sigma 2?
So with regard to sigma 2, we have, what is sigma 2 here? Right? So this is still going to be your an minus 1. But here we apply the same thing. We don't need this condition. The previous argument worked. We follow 9. This is an exact statement regardless of what conditions you have. I've got a little o of x here, a little o of delta x here. All right. My function. Okay. This is bounded. This is 1. So we don't have to worry. So little o of x times 1 is little o of x. This is little o of delta x. I got to write this as, so sigma 2 is using 9, right? We get little o of x for this part. This part is little o of delta x. But now I'm multiplying it by a chi of x over delta x. So that's of order of magnitude 1 over delta. This is of order of magnitude 1 over delta. If the chi function is x to the alpha, this is of order of magnitude 1 over delta to the alpha. Chi of x is like x to the alpha, and chi of 1 over delta is like 1 over delta to the alpha. So here I've got little o of this times delta to the alpha. But I still have delta to the 1 minus alpha there. And therefore, that is going to 0, because it's a positive power of delta, and delta is chosen small, so there is no problem there. Then as far as this is concerned, okay, I've got the, this is still the same thing, the total variation. So this is going to be little o of delta x times the total variation of the chi function on the interval 1 to 1 over delta. That's what this is. And that's, we choose the delta so that multiplied by the little o is still little o. So this is little o of x by choosing delta small. So this proves access theorem. So in all, you can apply this principle in many other settings.